Let's talk about how we can use image processing to find edges in an image. So to start with, we're going to talk about kernel operations. And to do this, we're going to use a really simple input image as an example. So this is just a 4x4 image we're going to use here as an example of what we might find in an input image in the real world. And we're going to pass kernels over it. So what is a kernel? A kernel is a small matrix that's essentially a window you pass over the image. So for our first example here, we're going to use a kernel that is 3x3, and each element is 1 over 9. So this is essentially going to average it, and you'll see how it works in just a second here. And using this kernel, we're going to create an output image based on that input image that's also a 4x4 image. Now you might notice that only the center 4 pixels in the output image are blank, and that's because we're actually not going to bother with the borders of the input image. We're not going to do any operations on the borders. We're going to use those pixels for some of what we're doing, but the methods that you use to calculate what happens at the borders are a little bit different, a little bit beyond what we're going to talk about in this class. So we're really just going to operate on these 4 pixels here in the center using the kernel there. So let's get started. We start by taking the 3x3 kernel and putting it over the 3x3 in the top left of the input image. So whatever size the kernel is, you put it in the top left of the input image. And then we're going to use the results of this to find the value of this pixel here, or the pixel that is essentially underneath the center of the kernel that we pass over the image. And what we're really going to do here is just a lot of math on the pixels underneath the kernel. So we take this 24 here, we multiply it by whatever is over it on the kernel, so 1 over 9. So we take 24 times 1 over 9, we add it to the pixel next to it, 200 times 1 over 9, and so on, so that we can get the value here. So if you're looking at this, you might think, well, this is really just summing up all the pixels underneath the kernel and then dividing by 9, which is the number of elements in the kernel. All we're really doing here is averaging it, and that's correct. That's why I started with this example here, because you can see how it works with a really simple example. So our pixel here is just going to be 24 times 1 over 9 plus 200 times 1 over 9 plus 18 times 1 over 9, and so on and so on and so on, and we'll get 99 as the final answer here, rounded to the nearest integer. Move to the next pixel here, so shift it 1 to the right, and really what we're going to do is take this kernel, start in the top left, shift it to the right 1 pixel at a time until it gets to the end of the image. In this image it's only 1 pixel, but in your image this will be much bigger. And then shift it down a row, and so on until we cover the entire image. So we just sweep this window over the entire image, performing this mathematical operation over the whole thing. And so we once again take this and say, okay, we're going to take 200 here, multiply it by 1 over 9, plus 18 times 1 over 9, plus 3 times 1 over 9, and so on and so on. We're going to end up getting 111 for this pixel here. We'll move the kernel to the bottom left of the image here and get 104 for that one, and the bottom right get 120. So what did we really do here? Well, we really just took these 4 pixels in here and we modified them so that they were the average of all the pixels around them, including them themselves. So let's put a little bit of mathematical notation on this. Let's call your input image F, your window W, and your output image G. What we just did there is G, x comma y, is equal to the convolution of W and F. So note that this is the convolution symbol, not multiplication. And what is the convolution? Well, this is the mathematical notation here. So basically what we do is pass the kernel over the entire image, taking each of the values of the kernel, multiplying it by the element of the image that's underneath it, and then adding up all those together to get the final answer for what goes in the pixel we're interested in. What we just did here is actually called a normalized blur, just an average. You can do this in OpenCV using cv2.blur. You give it the input image, and then you give it the size of the kernel you want to use. So in this case, we did a 3x3. You could easily do a 5x5, 7x7. Usually we use odd numbers because it makes it clear what the pixel underneath it is, but this is how you do a blur in OpenCV. Now how about a Gaussian blur? You might have heard of this before, but a Gaussian blur is very similar to the normalized blur, except that we have not just the normal values inside the kernel. So the basic kernel goes 1, 2, 1, 2, 4, 2, 1, 2, 1 across the whole thing. And what this does is it makes a nice little peak in the center of it, so that you end up with what often looks like a little bit more of a natural blur, or sometimes it actually brings out some of the features in it which is used for image processing. So what happens when we put this kernel over the image? Well, you'll see that these are still softened in here in these inner 4. They're not quite the same peaks and dips that they were before, but they're not quite the same as they were in the normalized blur either. Might be something you want to play around with in image processing to see what it does to the images you're playing with. In an OpenCV, we can do this with cv2.gaussian blur, note the capital letters here, and then again giving it the input image and the size of the kernel. So what if we want to do the opposite of a blur? What if we want to sharpen it instead? Well, if we sharpen it, then what we're essentially doing is taking the pixel in question here, multiplying it by a relatively big number to make it big in comparison to everything else, and then subtracting off its neighbors to try to make it different from its neighbors. And this is going to end up making extremes. So our small pixel value over here, 30, becomes negative 300, which will eventually get turned into 0 because we like numbers between 0 and 255. Our biggest value here, 189, is going to get turned into 507, and so on across the rest of the image. So the big numbers get bigger, the small numbers get smaller, and every so often you end up with one that stays about the same. Now let's actually talk about edges. And first off, we need to define what an edge is. So if you look at the left-hand side of this image here, if you're thinking about this image going from left to right, and you graph the intensity of it, well, we start out in white here, which is really high, like 255, and then we go into black, which is really low, like 0 or small numbers like that. Then we go back to white, which is 255 up here. So if you graph this, you end up with pretty obviously a strong negative derivative here, and then a strong positive derivative here. We generally call each side of this an edge, because each side of this is the image's intensity changing in some major way. And the point that we call an edge is often the extreme of the derivative, which if you remember back to calculus, the extreme of the derivative is found with the second derivative. So if we ended up taking two derivatives of the intensity of this image going across from left to right, then we would end up finding these two edges, one here and one here. So how do we do that using kernels? Well, we use the Sobel method of edge detection. So we have two different types of kernels for Sobel edge detection. We have the horizontal kernel, where we take all the pixels to the right of the pixel in interest and subtract them from the pixels to the left, and this is essentially approximating a second derivative. And then the vertical version, where we do the same thing, where we take the bottom pixels and subtract them from the top pixels. Like I said, this basically approximates the second derivative of the intensity of the image going either from left to right or top to bottom. And if you want to know from right to left, you can just reverse the horizontal one, and same thing with vertical if you want to go bottom to top. That's easy enough to do. You're just changing negative signs. So in OpenCV, you can do this with cv2.sobel. You give it the image, you give it the depth of the answer you want, the value for x and the value for y. So for a horizontal image, this ends up looking like cv2.sobel image, cv2, this is the notation for an 8-bit image like we tend to use, 1 for your dx because we're wanting to operate on x, and 0 for dy because we're not operating on y. This one, the 0 and 1 are reversed because we're not operating on x, but we are operating on y. So what does this look like? Well, if we take this original image here and we do the derivative just going across left to right here, we end up with this bottom image here. So going from left to right, these are the various edges where gray is not an edge, but anything more towards the white end is an edge, or black is a negative edge, so rising to falling. And if we go from top to bottom, we get the bottom right here, where again white is increasing and black is decreasing derivatives through the whole thing. And this image also includes Laplacian edge detection in case you're curious about that. Now we're not actually going to use Sobel edge detection for our purposes, but we are going to use Canny edge detection, which uses Sobel as one of its steps. And it's much more complicated, so we're not going to go too much into the math of it, but basically what a Canny edge detector does is it does some noise reduction using a 5x5 Gaussian blur. We did a 3x3 Gaussian blur earlier in these slides, and so you should be able to imagine what a 5x5 looks like. Then it goes through and finds the gradients using the Sobel method. Typically, you can actually choose what method you want, but we can just leave it at Sobel, which is the default. We remove some spurious edges using an algorithm that's a little bit complicated. And then we end up doing some thresholding on the edges. So we have a high and a low bar for the thresholding, and everything in the middle gets counted. And this is going to be your main tunable parameter as you're playing with the Canny edge detector. So how do you use the Canny edge detection in OpenCV? You do cv2.canny, and then you give it your input image, your low threshold, and your high threshold. What does this end up looking like? Well, if we take our sample image here and we apply Canny edge detection to it, we get this on the right. So note that this is independent of color here. So we're not caring if things are white or yellow, but we find some nice lines here around the lane markings, the yellow lines, the white lines, and so on. So this seems like something we can use going forward to build our lane detector. So let's review. Kernels operate over images using convolution. We basically do that by sliding the kernel over the image so that it operates on a given pixel using the values of its neighbors, and we can use these kernels to accomplish edge detection, which is one critical component in developing our lane detector.